So good morning, everyone. I'm Anna Effenberger.
I'm Nusha Agarwal.
I'm Tyler Lee.
I'm Jake Greenberg.
And I'm Vidya Dar.
And we are doing the fabrication characterization of polymeric aortic vessels. So there are four main components to our project. First, to identify a problem. Then our next steps were to learn about polymers through creation and characterization of them. This experimentation allowed us to explore the different avenues in which to treat the polymers to create our solution. And our final step was obviously to create our solution to our chosen problem. So our overarching goal was to create a 3D printed polymeric aortic vessel replacement for those suffering with connective tissue disorders such as Marfan syndrome. So connective tissue disorders affect the body's ability to create strong connective tissue. Connective tissue is necessary in almost the entire body. It gives skin its elasticity and it gives hair, nails, its strength. It's also necessary in intestinal tissues and blood vessels. Marfan syndrome is one of the most recognized connective tissue disorders, and it affects about 1 in every 5,000 people. One of the areas that affects many complications in this disorder is the aorta. The aorta is the first blood vessel in which blood leaves the heart. As such, it experiences the highest blood pressure. One of the complications in the aorta is called an aortic aneurysm. This is when the blood vessel is too weak to handle the blood pressure it experiences. As such, it expands and thins. If the walls thin too much, it can result in a tear. This is known as an aortic dissection, and you can see in the diagram there. This allows the blood to leak out of the vessel, and it quickly become fatal if left untreated. The current solution to this issue is known as the Dacron sleeve. This device is made of a Dacron mesh, which is a gelatin seal woven polyester, and it's attached via the sutures, as you can see in the diagram. It surrounds the patient's aorta. However, this device must be handmade, and this adds opportunity for human error and slows down the treatment process. Our proposed solution is a 3D printed aortic vessel replacement. This device aims to treat the patient while still in the aortic aneurysm stage before it dissects, and this is feasible in connective tissue disorders like Marfan syndrome, as these are diagnosed early in life. 3D printing allows the device to be customized quickly to the patient's specific dimensions, and the 3D printing files can be sent over the internet to a local printer and be printed within 12 hours using polymers.
Polymers are long chains of repeating units that are the fundamental building blocks of all natural materials. As you can see in figure 6, the first half of the image is repeated in the second half and will continue to repeat as long as the chain is elongated. Polymers can also be manufactured for biomedical purposes in a lab as long as they are treated with extra additives to broaden its applications. The connection between polymers and our solution lies within the 3 layers of the aorta: the intima, the media, and the adventitia. The intima and the media are the 2 inner layers of the aorta that are flexible and elastic. The adventitia is the one outer layer that's more rigid and protective, and it's a lot harder. Since the intima and the media shared similar characteristics, we decided to combine them into 1 layer for our model, and this would be mimicked by the polymer thermoplastic polyurethane, also known as TPU, which is also flexible and elastic. Polylactic acid, or PLA, was used to mimic the adventitia for its rigid and hard properties. To begin our research, we were given the differential scan calorimetry, or DSC scan, of PLA. The DSC scan helped us characterize the amorphous and crystalline structures in PLA as temperature was increased. It also provided us with the melting point of PLA, which is between 160 degrees Celsius and 180 degrees Celsius. To characterize the material that our device would need, we used extrusion, tensile strength testing, and X-ray diffraction. Unfortunately, since we were limited on time, we were only able to test these things on PLA and not TPU.
Okay, so our first step is to fabricate samples of polymer that were suitable for testing. So we performed an extrusion using an RH2000 rayometer. So how the machine works is, first we receive polymer in the form of powder or pellets. In our case, it was pellets PLA. We fed these pellets into the machine, and then the temperature was bumped until the polymer melts, which this is when the DSC scan came in handy. And then the polymer is extruded or pushed out of a nozzle and immediately cools. It comes out as strands of fiber. Using a separate machine, we drew these fibers at different speeds and then spooled them. In figure 10, you can see an example of one of our spooled fibers. So we tested 4 different grades of PLA. The first 3 grades were unsuccessful. They were too brittle to be spooled, like uncooked spaghetti. The last grade, 2003D, was successful. It was elastic and strong enough to be spooled, and and served as the grade of PLA that we used for the remainder of our experiments. Looking back, we found that the reason the first 3 were unsuccessful was not because of the difference in grade, but because they were older samples. They were about 3 years old compared to 2003D, which was more recently made. So another important result of our extrusion is that we were able to establish a relationship between the speed at which we drew the fibers from the rheometer and its resulting diameter. We found that this relationship was an inverse quadratic relationship. In figure 12, you can see a linearized graph of the relationship between speed and diameter. Essentially what you need to get out of this graph is that the r-squared values, the closer they are to 1, the more accurate this relationship is. Okay? So it's important to understand this relationship because in the future, when we need to create a fiber with a certain diameter, we know the speed to get what we want.
The next step in our testing process was to perform a tensile strength test in order to estimate how the given polymer would behave in the high tension conditions of the aortic region. In order to do this, we used a machine known as an instron, which essentially operates by taking our wide range of fiber samples, placing them between 2 clamps, pulling them until they're taut, and then starting a run. A run is essentially when the fiber is pulled until it either reaches a load of 2 newtons, until it elongates to double its initial size, or until it snaps. As this occurs, the instron is measuring stress and strain data. Stress is defined as the force applied to the fiber over its cross-sectional area, and strain is defined as the change in the fiber's length over its initial length. The ratio between stress and strain is something known as Young's modulus, which we can use to compare the stiffness of fibers. Stiffness is defined as how much force it takes to cause a fiber to stretch. The data produced by this came from the instron in different graphs originally. The original instron graphs had a linear part, a curved part, and a plateau part. However, Young's modulus is only important in the linear aspect, and when all that data came from the instron graphs, it ended up averaging out all of the data. So we Excel edited the data, we selected the linear part, graphed a linear regression line using its functions, and then we were able to see the r-squared values for how well that linear regression line fit to the selected data. As you can see, it was nearly perfect and therefore fit our purposes completely. Since, as you can see, all the slopes in figure 14 are relatively similar, it means that our controls, such as having an effective or initial length held between the clamps of each given polymer of 5 centimeters, these controls ensured that our experiments were similar every time, resulting in pretty much the same result that we thought we would see. So we then took the Young's moduli averages from each of sets of sample extruded at different temperatures and different speeds in sets of 3, and we compared them to their independent variables. Now, this is not enough data to make a true mathematical correlation between those factors in the Young's moduli. However, there is enough to state a given trend. The trend is that a higher speed, and therefore a thinner fiber, results in a higher Young's modulus, and therefore a stiffer fiber. One exception to that rule is indicated by an asterisk. This sample was annealed. Annealing is a process by which we take a fiber and heat it over a longer period of time. For us, it was 12 hours. This resulted in when we placed the initial load on the fiber, it snapped almost immediately, giving it a Young's modulus much less than the rest. Now, even though that fiber was extruded at a speed way beyond the rest of the other fibers, the effective speed on the Young's moduli was completely canceled out by the annealing process. So now we know that when we want a fiber, if, for example, a printer were to have functions similar to an extruder in the future, or if we were to take our own fiber and print it, we would want a relatively thin fiber, not too stiff so that it doesn't flex, and not too thin so that it snaps upon any tension. We would want a relatively thin fiber, and we wouldn't want to anneal the sample. However, we couldn't say exactly why we didn't want to anneal it. What is occurring in the annealing process that changes the Young's moduli of the fiber?
Following instron testing, we performed X-ray diffraction, which is essentially a process by which we use X-ray beams to ascertain certain aspects of the molecular structure. In this case, we wanted to determine what was the difference between untreated PLA and annealed PLA. So we mounted the samples by wrapping them around a piece of cardboard with a hole punched in it, then we put it into the detector, and then we turned on the machine. From there, a cathode ray tube produced a monochromatic X-ray beam, which from there was diffracted by the sample and then detected by a counter. So each beam's end location can be represented as a point on this scattering graph.
So this on the left here is a scattering graph of untreated PLA. And what we can see from this is it's a relatively diffuse scattering pattern, meaning that the structure of untreated PLA is relatively unorganized and amorphous. On the right, we can see a more well-defined and intense rings, meaning that this is a more defined scattering pattern. From this, we can conclude that the structure of annealed PLA is more organized and more crystalline. So we can integrate these scattering graphs, and from that we can produce graphs of intensity versus 2 theta. Now on the left we have the graph for untreated PLA, and as you can see, it's relatively amorphous because there are no crystalline peaks. The peaks you see here, this one is an amorphous peak. So this tells us that untreated PLA has relatively no crystallinity. On the other hand, we have annealed PLA, and as you can see, this is a very sharp and defined crystalline peak. Now, in order to calculate percent crystallinity, what we can do is we can take the area under this crystalline peak and divide it by the total area under the graph, and from that we can obtain the 27% crystallinity of annealed PLA. So what does this tell us? So annealed PLA is highly crystalline, which makes it brittle, which is likely the reason why it broke so readily in the instron, why it had a significantly lower elastic modulus. So this tells us that we wouldn't want to use annealed fibers in our sample or in our device because it would be very prone to breakage, especially in the high pressure environment of the aorta. Instead, we would want to use untreated PLA, which is both elastic and flexible, which is needed to accommodate the blood flow that goes through the aorta.
The next step in bringing our design to life is to create a three-dimensional blueprint for the aortic vessel replacement. This is done using a software known as Autodesk Inventor, which allows us to take a two-dimensional blueprint and extrude it into 3 dimensions. In figure 22, you'll see an iteration of design for something known as a C-clip, which we developed later on as an addition to our aortic vessel replacement. Figure 24 shows our complete design done in 3 dimensions, and it is composed of a main aortic vessel replacement, which is supposed to have 2 layers, the inner layer attempting to imitate the intima and the media with a flexible polyurethane, and the outer layer made of PLA meant to mimic the rigidity of the adventitia. As you can see, the C-clips that I mentioned earlier in figure 23 are a series of interlocking devices that come in pairs that are meant to cover the sutures to prevent further bursting due to the initial complications of Marfan syndrome, or if the device would be surgically implanted incorrectly. However, the device was also designed so that it is easy to surgically implant, which is why the clips are interlocking in the first place. Once we have this design, it's important to use all of the given professional tools you have at your disposal to make sure that people understand your design. What you see in figure 25 is known as a drawing, and it's a professional development tool used for showing the dimensions of the design you made. It showed how it's assembled, it showed when you have the dimensions, you can see its viability for 3D printing, how much fiber you may need, and it's not necessarily important to see the ridiculously small dimensions on this screen right now, but it is important to know that we can show designers, we can show doctors how the customization is implemented, what size is the aorta, and dispel the mystery around this thing we're going to be putting in somebody's body. Once we have this 3-dimensional design, it's compatible with 3D printing software. And the 3D printers that we use were a Lulzbot TAS6 printer and an Ultimaker 3. And the arrows indicate which aspects were printed. The polyurethane is in red and the PLA is in white. We printed 3 different versions of the polyurethane inner layer, one with the original dimensions, one scaled down by 5%, and one scaled up by 5%. We did this in order to test the tolerances, or how snugly each of those inner layers would fit in the outer layers, which is important when you're relying on a device for its sealing properties. In that same vein, however, polyurethane, when printed, turned out to be relatively porous, which would not be used in practice. The PLA prototype C-clips also came out, they work properly. However, you may notice that there's a slightly chamfered edge around each of these things that was not in the original 3-dimensional design. And this is due to an improper transferring of the STL or print files, which may have occurred when we send it off to a third party. However, the important part is that we do have a prototype, and these issues are relatively easy to fix, although we may like to go back to the drawing board and change the type of polymer used because, for example, PLA was a little bit too rigid for our purposes, polyurethane was too porous. We'd like to go back to the drawing board, talk to some more professionals, and maybe see if there are better polymers at our disposal that we can test.
So over the course of our project, we had many setbacks naturally. First, we were limited in our polymer choices. Initially, we were only giving 3 choices. Of the 3, we chose PLA. As previously mentioned, we had issues getting that CAD model to a 3D printable device. And by the nature of this program, we were limited to a 1-month timeline. If more time was given to us, we would perform more extensive material testing with a wider range of polymers. We would conduct in vivo testing, which essentially means testing within the body, to subject our prototype to the environment that a true aorta would be in. finally would have created a second version, maybe a third version of our 3D device. So a lot of information was thrown at you, but essentially what we accomplished during this project is, first we were able to choose a problem with the potential for a more effective solution. That was Marfan syndrome. Performed an extrusion which helps us establish that relationship between the drawing speed and then the resulting diameter of the fiber. XRD and tensile strength testing gave us the relationship between the thickness of the fiber and its Young's modulus or stiffness, as well as helping us understand the effects of annealing versus not annealing. We have a 3D printed prototype that you can play with later in our demo. And then, after reviewing our design, we do have improvements to make. But ultimately, we're a long ways away from having a marketable device. However, I think we have a solid foundation for future research.
So we would like to thank our project mentors, Dr. Murthy and Dr. MG, for guiding us through this process.
We'd also like to thank our RTAs, Pragya Huda, our project liaison, Brian Lai, research coordinator, and Nicholas Farrow, head RTA.
We'd like to thank the New Jersey Governor's School and all of its administration.
We'd like to thank Dean Rosen and Dean Antoine for providing this opportunity and mentorship.
We'd also like to thank Lockheed Martin, Silverline, Rubik's, and other corporate sponsors, as well as the GSAT alumni who continue to support us.
How do you propose to snap this device on the dissected aorta or the aorta which has an aneurysm? Because it's round and you can't thread the aorta.
Right, so
right?
what we would do is we would take the diseased part of the aorta, the part that has aneurysm, and essentially we would dissect it out of that part. Then we would insert our replacement, we would suture it to the patient's aorta and then connect it to our device. And then from there, it should simulate what an actual aorta's function is. And then the C-clips are meant to reinforce those sutures, because at times with certain biomedical devices, those sutures can be very prone to breakage and possibly leaking. So in order to compensate for that potential vulnerability, we made those C-clips so that they would be able to interlock and then prevent that from happening.
So the interior of the device, how do you prevent the blood that is going to come in contact with it clot? Because blood has this propensity, if it is going over a surface that's not its own, meaning body's own, it's foreign, it will clot. So did you guys think of what you would put on the interior to prevent that from happening, so that there's no thrombus formation on the device?
So, like I said, one of our future directions would be in vivo testing, which is testing within the body. Unfortunately, during our project, we didn't get to test all the biocompatibility issues of our device. I understand from what I've read and researched before that there would be a layer of things there are many options we can take to make it so that our device is interfaceable with the body.
In addition to that, we would also coat the surface with the patient's antibodies so that no clots would form, just to make it less foreign to the patient's body.
What imaging studies are you recommending to pull the specifications of the ARL?
I'm sorry, could you repeat that?
And what recommendations for an imaging study are you using to get the specifications of the ARL for printing, the size?
Okay, so currently we did have a little bit of difficulty with finding the dimensions. This is generally built for an average adult male's aorta. There's currently more imaging software and devices on the market. For example, I'm familiar with NVIDIA having produced a new way of taking a look into the heart. For example, we went to Thor Labs, and they're developing a lens with MIT to be able to look into the body without an MRI. That in combination with new AI that NVIDIA, for example, is producing would be able to estimate the rest of the way that the aorta might function, so we can get a more accurate picture of the inside. In terms of dimensions, like as specific as we can get, for a patient we would like to do that, but if we could do any regular dissections, there's probably lots of data out there about that we can average to use, for the general aorta size. I mean, otherwise, how would we make the Dacron sleeve currently? We would need to already know the dimensions. So that's not really a huge difficulty. We just didn't really look into it. Our project, although it does say biomedical device, we had a much greater focus on the polymeric aspect and how we could change the polymer aspects at their most basic level to be biocompatible.
Also, the paper that we referenced used a CAT scan, and they were on patients with Marfan syndrome, so we have an accurate measure of what the dimensions of the patient's aorta would be.
Can only take one more question.
What happens with all this data that you've collected now? Is there a progression so this isn't lost? Are there any programs that are going to be taking a look at this for its viability?
So our paper would be posted online, and we can always do that.
But like, so far we haven't like made any progress in like marketing it or commercializing it.